Hi, I'm going to give the presentation for our power electronics final project. And our project name is Asymmetric full bridge converter with high voltage gain. And our team have Ying Yuxuan, Li Yishun, and Hu Yifan, and my name is Hu Yifan. Here is our talk agenda. Me, Hu Yifan, will introduce the basic information for this project, including the abstracts, some background information, and the introduction for the model. And then Ying Yuxuan will explain how to design the parameters of the model and how it works. And he will give the simulation results, screenshots, and illustrate every element's principles. So we can figure out how the model exactly work. And then the Yishun will analyze the results we generate by running the model and then make the timeline table for this project. And here is the abstract for our project. Our project is to propose an asymmetric full bridge converter. We will calculate all the elements in the circuits according to the paper we find, and we will illustrate it step by step in our report and presentation. And then after getting these calculation results, we will use Simulink to simulate the model, and then we will run the model and get the results. And then we will compare the simulation results with the theoretical one to see the difference and simulations, so that we can base on the result to draw some conclusions and have some suggestions to improve our model. And as what I said, our model is called asymmetric full bridge converter. So we should find some paper and read so that we can understand how the operation rule of this model. And then we have to design the parameters and build the circuits in Simulink to meet the demand of our output power. And our desired power is 10 kilowatt, and the efficiency must higher than certain value, and so on, like the voltage ripple or current ripple, some specific demand. And then we will find all the elements in real life according to the experimental results. Since if the elements we design does not exist, there is no meaning. So we try to find all the elements in real life. And the last objective is to know the application of this model in industries, such as mobility applications and renewable energy systems. And then I will give you the background of this project. In modern society, the demand of step-up DC-DC converters is increasing because these converters can applied well in some industries, such as fuel cells uh, and mobility applications. But the conventional structure of converters, such as flyback converters or non-isolated converters, have certain problems, so that they could not meet the demand of the society. For example, In flyback converters, the additional inductors and filter capacities need to be added to have static voltage gain. But in that case, the cost and the voltage loss is very high, so it is not practical. And in non-isolated converters, the size is too big to use in embedded system, and also the switching losses are too high to endure. So these structures cannot be used in real life in high demand situations. So our group proposes a symmetric full-bridge DC-DC converter to avoid the problems mentioned before. And here is the chart to compare the conventional converter to the model we propose. And we can easily see the potential problems of the conventional converters, and they could not realize zero current transition or zero voltage transition. But in our model, the voltage gain is high and then the switching losses is low, and all the demands can be met. So if we can really realize the model in real life, it will have big applications. And then Yingxuan will introduce how to design the parameters and how to simulate in the Simulink.
Hello everyone, I'm Yingxuan, majoring in electrical engineering. I'm very glad here to present the proposed design of our project. Please look at the picture on the left. It's the topology of our circuit. On the left side is a full bridge with 4 thin MOSFETs and a clamping capacitor. And in the middle is a transformer. With certain temperature, the voltage is boosted. And for the second stage is a voltage doubler, which will double the voltage from the transformer. And here is the ideal output of our design, referring to some papers. You can look at here. The capital D is the duty ratio, and TS is the switching time period. During DTS, two MOSFETs is on, and the other two is off. And on the right side of the one period, the other two switches are on, and those two are off. And for the key waveforms, we want to focus on the voltages on switches and the current on the diode. As you can see, because we need them to be zero voltage switching and zero current switching. So that's the most important waveform we want to focus on. VS1 to VS4 and IBO1 and IBO2. Then I will introduce how we calculate the parameters for the element used in the circuit. First is the Dmax and N. From the relationship between voltage gain and N, K, and D, we can easily calculate the D and N by MATLAB. The result is shown here, consider N equal to 3, because we want it as should be an integer, and the K and D is calculated. Then we also want to introduce how we select the parameters for Ls and Ln. For Ls, it's quite easy with this equation, which is dependent by the IO max, the maximum output current. And Ln can be determined by the assuming the energy difference stored in them in Ls and Ln should be larger than the energy stored in C1 and C4. And by this equation, We can easily carry the assumed LF and LM here. It's also done by MATLAB. Then we want to calculate the value for CC. It's depend on the report voltage on the left side of the transformer. That's the first stage. By solving these three equations, we can easily calculate by the MATLAB, and that is value for CC is 4.7 millifarads. And we also want to calculate the value for CO1 and CO2 depending on the ripple of the voltage on the right side of the transformer as the output voltage of the whole circuit. Because we want the voltage ripple, it should be smaller than 1 voltage. And we plug all the value for B and TS. We can usually calculate the final value for these two capacitors. The value is 22 millifarad. Okay, after we have selected the value for L and C, we can build a MATLAB simulation model and plug all the parameters in, and we add many different voltage measurements and current measurement in this circuit, so that we can look into the scope and get what we want, the waveforms of those voltages and the current. So the assumed outcomes of our simulation is the input output voltage and current, and the voltage current plots on the side, and the switches because we want to look at it to see if it's zero voltage switching or zero current switching. And the detailed plots and discussion on them will be shown later by my teammates Lishan. And let's welcome Lishan to give you the rest of our presentation.
In this part, let's see the model built by Simulink. And first, as for the structure, we have 4 power switches S1 from S1 to S4, and 1 collecting capacitor, and 1 transformer in the middle. And on the secondary side, we have the voltage double structure and 2 output diodes and 2 capacitors to increase the voltage gain with the voltage rise on the diode is constrained. And besides, we have a pulse generator control to generate different pulse waveform with different duty cycle. As for the results discussion, and the first one is the current or voltage source and the output voltage. As we can see, the voltage source is 48 volts, and the input power is the input power is around 10 kilowatts. And by our calculation, the voltage gain is calculated as 6.67. The ripple voltage is less than 1 volt. And in this figure, we can do some analysis of zero voltage switch performance of the power switch. In this slide, we show the current and the voltage of power switch 1. As we can see, the performance is changed with the new middle stage of voltage. Therefore, it means the simulation result is not perfectly the DVS situation. As the same status in DCS performance in power diodes on the secondary side of the transformer. The performance also not very well. And as for these results, the simulation of our model is relatively okay, not very perfect, but because but it still meets the requirements of our some objectives such as voltage gain, and it has a small ripple voltage, and the maximum output power is around 10 kilowatts. And for the future performance on ZCS and GVS, we are looking forward for less power loss, because on the circuit we built, it enlarged our power loss, so we need more modifications on that. This is our timeline and Gantt chart of our project. And for the review and the future, in this project, we think we learned a lot of useful skills, such as using Simulink and some analysis and calculation of the circuit operation in different modes. We consolidate our course knowledge from power electronics. But in the future, we think we have more modifications on the parameter selection to do, which will help us to have a better performance on the DVS and the GCS result. And we are hoping to build a real circuit in practical. As for conclusion for this project, we designed an asymmetrical DC-DC converter with Simulink, and the characteristic for this design are having relative good performance on voltage gain and specific switching frequency, and the power loss is acceptable, and the voltage drop is not very big to destroy the diodes. So though our simulation result is not very good, is not perfect, but we wish we could learn more and do more simulation if we have more time in the future. Anyway, the goal of this project is achieved because we have learned some new knowledge and review the basic concepts we learned from the course. Here is our reference. So thank you for listening.